Data moves fast, but it cannot outrun the speed of light. Content delivery networks exist to solve this specific physics problem, though treating them as static storage ignores their capacity for edge logic. Today's CDNs are fully programmable, globally distributed networks. If a user in India requests data from a server in the eastern United States, that packet crosses thousands of miles of underwater fiber. Even in ideal conditions, that round trip can easily exceed 300 milliseconds. Amazon CloudFront solves this geographical penalty by intercepting the request at the nearest point of presence, or POP. Instead of traveling across the globe to negotiate a secure connection, the TLS handshake is terminated locally, slashing the initial connection time. This architecture diagram shows CloudFront's topology. Traffic flows from viewers into edge locations. If content isn't paged, it moves into mid-tier regional edge caches, which act as a massive consolidation layer shielding the origin from traffic spikes. Storing public HTML and images at these edge nodes is trivial. The actual engineering challenge is taking private, monetized content, like premium video streams or restricted data, and enforcing strict security access without breaking the speed of this edge cache infrastructure. If your origin is a public Amazon S3 bucket, all the CDN security in the world won't protect you. Attackers can simply bypass CloudFront, query the S3 bucket directly, steal the content, and stick you with massive egress data transfer bills. To close this, AWS introduced Origin Access Control. CloudFront dynamically generates a signature version 4 header, attaching it before forwarding. Your S3 bucket policy is then configured to reject requests lacking that signature, verifying the AWS source ARN matches your exact CloudFront distribution. By demanding cryptographic proof on every fetch, OAC effectively air-gaps the origin from the public internet. All traffic is now forced to prove its legitimacy at the edge. With the origin isolated, the next problem is user authorization. We need to restrict access for individual viewers right at the edge location, without pausing to query a central backend database, which would instantly reintroduce the latency we just eliminated. We achieve this decentralized authorization using signed URLs. The backend server creates a JSON policy containing restrictions like an expiration timestamp and an allowed IP. It then signs that policy using an RSA private key. CloudFront holds the corresponding public key, allowing it to validate the signature locally. When a user clicks a signed link, CloudFront verifies the signature and expiration, routing the authorized request to the cache node. If a user tampers with the URL's expiry timestamp, the hash breaks. CloudFront instantly returns a 403 forbidden error without waking the cache node. Signed URLs empower the edge to make instantaneous, cryptographically guaranteed access decisions completely autonomously. This model works for a single download, but modern video streaming protocols like HLS and Dash slice media into thousands of sequential chunks. Generating a unique RSA signature and query string for every single one of those video chunks requires massive backend CPU overhead. Worse, because every URL is dynamically generated, the browser treats them as unique files, destroying client-side caching. To fix this architectural bottleneck, we shift the authorization burden from a per-file model to a per-session model using signed cookies. Instead of signing individual files, the backend issues a custom policy containing a wildcard asterisk. This allows a single browser cookie to authorize access to an entire directory of media segments. The player requests the chunks using clean, static URLs. The browser caches them normally, and CloudFront validates the cookie in the background. Signed cookies allow private media delivery to reach millions of concurrent viewers without overtaxing the origin. This brings us to a pervasive engineering misconception. Many developers assume that if a file is already sitting warm in the CloudFront cache, an expired link will somehow still serve that file. If a URL expires in 5 minutes, but the cache TTL is 1 hour, a request at minute 6 is instantly blocked with a 403 error, despite a warm cache. Conversely, a valid URL at minute 10 passes authorization, but if the cache node evicted the file, it forces a fresh origin fetch. The inverse can also happen on the client's local machine. If your application sends aggressive cache control headers, the browser might serve the video segment straight from its own disk, bypassing CloudFront's URL expiry entirely. To prevent unique signature strings from creating duplicate cache entries, CloudFront strips out the signature, policy, and key pair ID parameters from the URL before hashing the path into the final cache key. Edge authorization and edge caching are strictly decoupled lifecycles. The cryptographic security is always evaluated first, and the cache is only consulted if the math checks out. Because the cache key determines if a request hits or misses, forwarding unnecessary data like marketing tracking parameters into your cache policy will severely fragment your storage and destroy your cache hit ratio. When realizing their cache is fragmented, a developer's first instinct is often to trigger a brute force wildcard cache invalidation. This forcefully purges edge nodes globally, sending a massive spike of traffic back to the origin and rapidly driving up invalidation costs. The high-performance, zero-cost alternative is standard file versioning. By appending a version hash to the file name, like main.v2.js, you force the client to fetch the new asset immediately, leaving the old cache to expire naturally. Disciplined cache key management and strict file versioning are required operational practices to protect the origin from traffic spikes and keep your delivery costs under control. This diagram illustrates how all these components synthesize into a production-grade streaming pipeline. We layer the authorization logic over the CloudFront distribution itself, securing the content flow as it moves out from the AWS Elemental Media Services and through the caching tiers. To execute this logic, we use edge compute. AWS offers two distinct environments for running custom code directly on the CDN: CloudFront Functions and Lambda at Edge. This table shows where each tool excels. CloudFront Functions run at the viewer phase in under a millisecond. They are highly constrained, strictly executing JavaScript for lightweight tasks like JSON Web Token validation or rapid cache key normalization. Lambda at Edge is reserved for heavier lifting at the origin phase. Because it allows full network and file system access, you can run complex Node or Python scripts, like dynamically querying Route 53 to execute a multi-region origin failover. By injecting these compute functions directly into the request lifecycle, you create a delivery pipeline that can handle millions of requests per second while maintaining strict cryptographic isolation. When deploying these architectures, the most common and frustrating failure state is configuring your secure distribution, deploying your code, and immediately hitting a wall of 403 access denied errors. There are three primary configuration issues to check first. Ensure your origin access control policy is perfectly aligned with your S3 bucket. Verify that the custom policy strictly matches the exact protocol, including the HTTPS prefix. Finally, check your header parameter ordering. The CloudFront signature must be the first value in the set cookie header, or the browser will fail to parse it. This leads to a classic senior architecture interview question. If a user's account is compromised, how do you revoke a specific signed cookie before its natural expiration time? Because native revocation does not exist in the CloudFront specification, you cannot simply delete a token. Instead, you must deploy an AWS Web Application Firewall combined with an edge compute function to actively cross-reference incoming requests against a dynamic, distributed block list. Final thought. Mastering the edge means treating it as a programmable extension of backend logic. By tightly controlling cache keys and cryptographically isolating origins, you build systems that scale to global audiences without compromising security or performance.